Chapter 1 Principles of Operation. In the technical literature, diesel power plants are known as compression ignition engines, CI engines. Their gasoline counterparts are of the spark ignition variety, SI. This idea of compression ignition is essential to understanding a diesel engine. When a given amount of any engine is compressed into a smaller volume, its pressure and temperature rise. The increase in temperature is in direct relation to the rise in pressure, which is directly related to the degree of compression. That is, the rise in temperature is the result of compressing the existing gas into a smaller space, rather than by the addition of extra heat. For a better understanding, imagine two heaters with exactly the same output. Each has been placed in a separate room. To begin with, both rooms are the exact same temperature, but one is twice the size of the other. Both heaters are turned on. The small room will heat up faster than the large one, even though the output from the heaters is the same. In other words, although the same quantity of heat is being added to both rooms, the temperature of the smaller one rises faster because the heat is concentrated into a smaller space. This is crudely analogous to what happens when the gas is compressed. At the onset, it is given volume and contains a certain amount of heat. As the gas is compressed, this quantity of heat is concentrated into a smaller space, and the temperature rises, even though there is no more heat being added to the gas. Compression ignition. All internal combustion engines consist of one or more cylinders that are closed off at one end and have a piston driving up the other. In a diesel engine, air enters the cylinder, then the piston is forced up into it, compressing the air. As the air is compressed, the heat contained in it is concentrated into a smaller and smaller space. The pressure and temperature rise steadily. In the compression ignition engine, this process continues until the air is extremely hot, say around 1,000 degrees Fahrenheit or 538 degrees Celsius. This temperature has been attained purely and simply by compression. See Figure 1-1. Diesel fuel ignites at around 750 degrees Celsius or 399 degrees Celsius. Therefore, any fuel sprayed into a cylinder filled with air superheated to 1,000 degrees Fahrenheit is going to catch fire. This is exactly what happens. At a precisely controlled moment, fuel is ejected into the cylinder and immediately starts to burn. No other form of ignition is needed. To attain high enough temperatures to ignite diesel fuel, air generally has to be compressed into a space no larger than 1/14 of the original size of the cylinder. This is known as a compression ratio of 14:1. The compression ratio is the volume of the cylinder when the piston is at the bottom of the stroke, relative to the volume of the cylinder when the piston is at the top of the stroke. See Figure 1-2. Most diesel engines have compression ratios ranging from 16:1 to 23:1. This is much higher than the average gasoline engine's compression ratio of 7:1 to 9:1. The lower compression ratios of gasoline engines produce lower cylinder pressures and temperatures. As a consequence, the ignition temperature of gasoline is not reached through compression, and the gas-air mixture has to be ignited by an independent source, a spark. Hence, the designation spark ignition for gasoline engines. Converting heat to power. I've established that when a gas is compressed, its temperature rises. It is also true that when a gas is heated in a sealed chamber, its pressure rises. In the first instance, no heat is added. The existing gas is merely concentrated into a smaller space, thereby raising its temperature. In the second instance, heat is added to the gas that is trapped in a closed vessel, and this causes the pressure to rise. This is what happens during ignition in an internal combustion engine. A body of air is trapped in a cylinder by a piston and compressed. The temperature rises. Fuel is introduced by some means and ignited. The burning fuel rises the temperature in the cylinder even higher, and this rises the pressure of the trapped gases. The increased pressure is used to drive the piston back down the cylinder, resulting in what is termed the piston's power stroke. The engine has converted the heat produced by the burning fuel into usable mechanical power. For this reason, internal combustion power plants are sometimes known as heat engines. It is possible to calculate the heat content of the fuel by measuring how many BTU, or joules in the metric system, are produced by burning a given amount, such as a gallon or liter. An engine's horsepower, HP, rating, or kilowatt in the metric system, can be converted to a BTU or joules. For example, 1 horsepower equals 2,544 BTU. In this way, the heat energy going into an engine, the number of gallons or liters burned per hour, times the BTU or joule content of the fuel, can be compared with the power being produced by it. This enables the thermal efficiency of the engine to be determined, i.e., how much of the fuel's heat energy is being converted to usable power. The average diesel engine has a thermal efficiency of 30 to 40%. In other words, only about a third of the heat energy contained in the fuel is being converted to usable power. Roughly half of the remaining 2/3 is lost through the exhaust system in the form of hot gases. The rest is dissipated into the atmosphere through the cooling system and by contact with hot engine surfaces. See Figure 1-3. As wasteful as this sound, diesels are still considerably more efficient than gasoline engines, which have a thermal efficiency of 25 to 35%. Expansion and cooling. Just as compressing a gas raises its temperature, so too can the pressure lower the temperature. This is due purely to the expansion of the gas into a larger space or volume, not to any loss of heat. The greater the reduction in pressure, the lower the resulting temperature of the gas. As a piston moves down on its power stroke, the volume inside the cylinder increases, causing a fall in pressure and consequently a fall in temperature of the gas in the cylinder. These declining temperatures reflect the heat of combustion being converted into mechanical power, i.e., the movement of the piston. See Figure 1-4. The higher the compression ratio of the engine, the greater the expansion of gases on the power stroke. In an engine with a compression ratio of 22:1, for example, the gases will expand into a volume 22 times the size of the compression chamber. In an engine with a compression ratio of 7:1, the degree of expansion will only be 7 times greater. Since the temperature drops as the gas expands, diesel engines, because of their higher compression ratios, are able to convert more of the heat of combustion into mechanical power than their gasoline counterparts. Hence, diesels are more thermally efficient than gasoline engines. Gasoline engines. You might well ask, why not increase the compression ratio on the gasoline engine and thereby improve efficiency? A gasoline engine draws in fuel with its air supply before compression, either through a carburetor or through a fuel injection into the inlet manifold, not the cylinder. A diesel, on the other hand, has the fuel injected after the air has been compressed. Increasing the compression ratio for a gasoline engine would raise its compression temperature beyond its ignition point of gasoline, which would lead to a premature combustion of the fuel-air mixture. This would rapidly wreck the engine. To avoid this, the compression ratio on the gasoline engine must be kept low, and the fuel-air mixture must then be set off by a spark at the appropriate moment. This accounts for the need of an electrical ignition system on these engines. On occasion, gasoline engines can become sufficiently overheated to cause the fuel-air mixture to ignite before it should. This is known as auto-ignition or pre-ignition, and most often occurs when the overheated engine is turned off but refuses to quit, even though the ignition has been turned off. You might next ask, why not jack up the compression ratios on gasoline engines and use fuel injection directly into the cylinders to prevent premature ignition, just as is done on a diesel? Apart from the obvious fact that you now have a diesel engine to all intents and purposes, you might as well use the often cheaper diesel fuel. You run up against the nature of gasoline itself, which is far more volatile than diesel. Even though a diesel engine may be turning over at 3,000 RPMs, revolutions per minute, with the power stroke of any one piston lasting no more than 1/100th of a second. The injection diesel fire fuel burners at a controlled rate rather than exploding. Indeed, if it fails to burn at the correct rate, ignition problems result and engine damage is likely. Because of its greater volatility, the same degree of control cannot be maintained over gasoline. Explosive combustion would occur, destroying the high compression power plant. The gasoline engine, at the current level of technology, is therefore locked into lower compression ratios and decreased thermal efficiency. Cost and power to weight. Because diesels feature higher compression ratios than gasoline engines, they are subjected to greater stressors and must be built more ruggedly. To sustain these higher compression ratios and loads, diesels generally have to be machined to closer tolerances. The heavier construction and closer mechaning tolerances account for the increase in weight and price of a diesel engine over gasoline engines of the same power output. In recent years, however, tremendous advances in metallurgy, and engine design have achieved drastic weight reductions on many diesels, considerably narrowing its power-to-weight gap. Types of diesels. Diesel engines can be 4-cycle or 2-cycle. The differences will become clear in a moment. Let us first look at a 4-cycle engine. A 4-cycle diesel. 1. Imagine the piston is at the top of its cylinder. The inlet valve opens as the piston descends to the bottom of its cylinder. The descending piston draws air into the cylinder. When the piston reaches the bottom of its cylinder, the inlet valve closes, trapping the air inside the cylinder. See Figure 1-5. This movement of the pistons from the top to the bottom of its cylinder is known as a stroke. It also constitutes one of the 4 cycles of the 4-cycle engine. In this case, the suction, induction, or inlet cycle. 2. The piston now travels up the cylinder, compressing the trapped air. The pressure rises between 450 and 700 pounds per square inch. PSI as compared to 80 to 150 PSI in a gasoline engine, and the temperature to 1,000 degrees Fahrenheit or more. This is the compression cycle. 3. Somewhere near the top of the compression stroke, fuel enters the cylinder via the fuel injector and starts to burn. The temperature climbs rapidly from 2,000 degrees Fahrenheit to 5,000 degrees Fahrenheit. This increase in temperature causes a rise in pressure to around 850 to 1,000 psi, pushing the piston back down its cylinder. As the piston descends, the cylinder volume increases rapidly, leading to a sharp reduction in the pressure and temperature. This is the 3rd cycle and is known as the power stroke. 4. When the piston nears the bottom of the power stroke, the exhaust valve opens. The cylinder still contains a considerable amount of residual heat and pressure, and most of the gases rush out. The piston then travels back up the cylinder, forcing the rest of the burned gases out of the exhaust valve. This is the fourth, or exhaust cycle. At the top of the exhaust stroke, the exhaust valve closes and the inlet valve opens, ready to admit a fresh change of air when the piston descends the cylinder once again. This brings the engine back to the starting point of the 4 cycles. A 2-cycle diesel. Note, the following is the description of the operation of a Detroit diesel 2-cycle engine, the most common and widely known type. There are engines with other forms of 2-cycle diesel operations, but such engines are unlikely to be encountered in small boat applications. A Detroit diesel 2-cycle engine operates in essentially the same manner as a 4-cycle engine, but condenses the 4 strokes of the piston into 2. Once up the cylinder and once down. Here's how. 1. We start with the piston at the top of the cylinder in its compression stroke. The cylinder is filled with pressurized, superheated air. Diesel is injected and ignites. The piston starts down the cylinder on its power stroke. As it descends, the cylinder pressure and temperature fall. When the piston nears the bottom of its power stroke, the exhaust valve opens and most of the burned gases rush out of the cylinder. See Figure 1-6. So far, all of the same as the 4-cycle diesel. Now, as the piston continues to descend the cylinder, it uncovers a series of holes or ports in the cylinder wall. A supercharger or turbocharger blows pressurized air through these ports, pushing the rest of the burned gases out of the cylinder and refilling it with fresh air. The piston has only now reached the bottom of its cylinder and is starting back up again. The exhaust valve closes. 2. As the piston moves back up, it blocks off the inlet ports, trapping the charge of fresh air in the cylinder. Although the piston has only covered a little over 1 stroke, it has already completed its power stroke, the exhaust process, and the inlet cycle. As the piston comes back up the cylinder on its second stroke, it compresses the fresh air. When it reaches the top of the cylinder, injection and combustion takes place. The cycle starts over. The engine has done in 2 strokes, what a 4-cycle diesel does in 4. A 2-cycle engine has 2 power strokes for every 1 power stroke of a 4-cycle engine. For a given engine size, a 2-cycle engine develops considerably more power than a 4-cycle. This leads to lower cost per horsepower and improved power-to-weight ratios. A 2-cycle diesel, however, is less thermally efficient than a 4-cycle and has higher fuel consumption, resulting in higher levels of exhaust pollution. The life of a 2-cycle diesel tends to be shorter than that of a 4-cycle model because of the higher loads placed on the engine. What's more, for reasons that will become clear later, 2-cycle diesels tend to be far noisier in operation than 4-cycles, which makes them unsuitable for a wide range of pleasure boat applications. In recent years, tightening emission regulations have pretty much put an end to the manufacture of the 2-cycle diesels. Principal engine components. The crankshaft. So far, I've talked in a purely abstract fashion of a piston moving up and down in its cylinder. To harness a piston to the rest of the engine and to utilize the mechanical energy developed by its power stroke, this reciprocal motion must be converted to rotary motion. This is done by a crankshaft and connecting rod. A crankshaft is a sturdy bar set in the bearings at the base of an engine. Beneath each cylinder, it has an offset pin forming a crank. The connecting rod ties the piston to this crank. A bearing at each end of the connecting rod allows the crank to rotate within the connecting rod's lower end, while the piston, mounting on a piston pin or wrist pin, oscillates around its upper end. As the piston moves up and down, the crankshaft turns. See Figure 1-7. Valves and timing. This effective operation of four-cylinder and two-cycle engine requires the precise coordination of piston movement with valve opening and closing times, as well as with the moment of fuel injection. This is known as valve and fuel injection timing. Valves are set in cylinder heads and held in a closed position by a valve spring. A lever known as a rocker arm opens the valve. The rocker arm, moved up and down directly or indirectly by a camshaft, pivots in the top of the cylinder head. See Figures 1-8 and 1-9. A camshaft has a series of elliptical protrusions, or cams, one for each valve in the engine, along its length. As the camshaft turns, these protrusions push the rocker arms up and down. Some camshafts are set in cylinder heads with the cams in direct contact with the rocker arms. These are overhead camshafts. Others are placed in the engine block and actuate the rocker arms indirectly via push rods. A gear key locked to the end of the crankshaft rotates with it. Another gear key to the engine of the camshaft rotates with it. The valve timing, or valve opening and closing times, is coordinated with the movement of the pistons by linking to the two gears with an intermediate gear, a belt, or a chain so that they rotate together. See Figure 1-10. On a four-cycle engine, the inlet and exhaust valves open and close on every other stroke of the engine. As a consequence, the gear on the camshaft is twice the size of that on the crankshaft, causing the former to rotate at half the speed of the latter, and the valves to open and close on every other engine revolution. Detroit diesel two-cycle engines have only exhaust valves. The exhaust valves open on every downward stroke of the piston. Therefore, the camshaft gear is the same size as that on the crankshaft. The two shafts rotate at the same speed and the valves open and close on every engine revolution. By setting the camshaft and crankshaft gears in different relationships with one another, the valves can be made to open and close at any point of the piston travel. Timing engine valves consist of placing the gears in the precise relationship needed for the overall maximum engine performance. Conventional mechanical fuel injection timing is set the same way. Electronic may be different. A gear fitted to the end of the fuel injection pump drive shafts is driven by the crankshaft via an intermediate gear, belt, or chain. Altering the relationship of the gears allows the moment of fuel injection to be set at any point of piston travel. Since injection occurs on every other revolution on a four-cycle engine, the pump drive gear is twice the size of the crankshaft gear, causing the pump to rotate at half the engine speed. On two-cycle engines, the gears are the same size, producing injection at every engine revolution. Cylinders and other parts. The central frame to which the rest of the engine is assembled is known as the block, or crankcase. See Figure 1-11. On all except air-cooled engines, which are rarely found on boats, this is a casting containing numerous passages for air, cooling water, oil, and other engine parts, such as the crankshaft and camshaft. There are two types of cylinders or liners available for diesel engines: dry liners and wet liners. In a dry liner diesel, the cylinders and block are in continuous metal-to-metal contact. In a wet liner arrangement, the block comes into contact with the cylinders only at the tops and bottoms. The engine cooling water circulates directly around the liners. See Figure 1-12 and 1-13. Wet liners have the advantage of being relatively easy to replace in the field when a major engine overhaul is necessary, whereas to change dry liners, the whole block must generally be taken to the machine shop. Pistons are fitted with a number of piston rings set in grooves cut into the outside circumference of the piston. The piston rings press out against the walls of the cylinder to make a gas-tight seal. The top end of the cylinder is sealed with a casting known as a cylinder head, which contains the injectors, valves, and frequently combustion chambers, water passages, and so on. The valves are set in guides, which are replaceable sleeves pressed into the cylinder head. When an engine begins to show appreciable wear, these valve guides can be pressed out and replaced. Better quality engines also have replaceable valve seats, the area that the valve contacts to seal the combustion chamber. Remaining valve seats, replacing valve guides, and installing new valves renew the cylinder head, giving the expensive part of an almost indefinite life. See Figures 1-14 and 1-15.